Hello dear students, welcome you all. In this lecture, I am going to discuss about the experimental verification of experimental verification of Maxwell's Boltzmann distribution law of molecular speeds. Right. So here in this article, we are going to discuss how Maxwell-Boltzmann distribution law of molecular speeds was experimentally verified. Right? We know what was the expression of this Maxwell-Boltzmann distribution law of molecular speeds. It was mv dv is equal to 4 pi n m upon 2 pi k t, right, power 3 by 2 into b square into e raised to power minus m b square upon 2 k t dv, right. This was the Maxwell-Boltzmann distribution law for molecular speeds. Clear? Now we are going to uh, discuss about an experiment that verify this equation, right. This equation basically tell us about the number of gas molecules that has velocity in the range of v to v plus dv. Clear? Here there are different factors on which this value depend. Mainly depend upon temperature, velocity, and this exponential factor. This again depend upon temperature, mass, and velocity. Right. When Maxwell and Boltzmann derived this equation, then after there was a need for the experimental verification of this equation, whether the distribution of molecular speeds is in accordance with this equation or not. We have seen the graph. We have seen the graph, and that graph was, uh, I can recall that graph that give us the variation of this, number NVDV with the velocity, right? So that graph was of V, and this was n V upon n, right? So that graph was like, right. Here we can see from this graph also that at a given temperature T, the most of the gas molecule will try to remain within a particular range of velocities. Clear? The molecule toward this side are very low in number. Again, the molecules toward this side are very low in number. So most of the molecule will possess this band of velocities, right. We have also found the expression for v rms, v average. Clear? And v most probable. Most probable means the velocity possessed by most of the gas molecules, right. Now there was a need to experimentally verify all these things. So several experiments were performed to verify all these, equations, theoretical predictions. The one experiment that completed this task was an experiment performed by IF Jartman and CC Co. Clear? In 1930. Clear? Their experiment verify all the theoretical predictions of this equation, right? Now I'm going to discuss about this experiment of IF Jartman and CC Co. Right. For that, now I will first of all take the schematic diagram of the experimental setup that they have used for it. Clear? So their experiment consists of a highly evacuated chamber, right? You can see here it consists of a oven at the bottom of this chamber, right? Then there is a drum at the top of this oven. So I'm going to show all this. So this is connected to the vacuum pump, toward the vacuum pump. Clear? Uh, this is highly evacuated chamber so that all the air present inside this chamber has been removed with the help of this vacuum pump, right? And this is a oven, clear? Heating oven that contain a particular material. Here in this particular case, sorry, the material that they have taken was bismuth, clear? So it is bismuth in liquid form. It is heated continuously with the help of a filament oven. Yeah. So it is bismuth in liquid form. So when bismuth is heated continuously, it will convert into vapor form, right? And then finally these vapors will come out of from this slit, right? This opening. So here we have placed a slit, yeah, in order to make a fine beam of these bismuth atoms. Clear? So here we have placed a slit, right? So this is actually fine opening here. You can see only very fine opening slit. Yeah. So the bismuth atom, this is slit S2. Clear? And this is source. This is a source of atoms. Source, and it is bismuth. Bismuth. Clear? It is open. And here we have a drum, fastly rotating drum. So Yeah, this is the fine beam of bismuth atoms that is coming out of this open, right, through this very fine slit. Clear? And here we have a fastly rotating drum. Clear? That drum is rotating at very high speed. Clear? It is clear. So this is actually a drum here. This is rotating in this direction or in this direction. Let's assume that it is rotating in this direction, and it is a very fine opening here in the drum, right? This is called slit S1. Clear? So that the bismuth atoms can enter uh, inside this drum, hollow drum, through this slit, right? Here, exactly opposite to this slit, we have a glass plate attached here. Clear? We have attached a glass plate here. Clear? So that the atoms can deposit here. They can collect here. Clear? You can see here. Right. This is the drum. It is rotating at very high speed. It is actually connected through a motor, electrical motor. So it is rotating around 6,000 runs per minute, RPM. Right? This is vacuum pump. This is a glass plate. Right. Now this is the schematic diagram of this entire experiment. Right. Now what is the principle of this experiment? Principle is very simple, right? When a beam of molecules or atoms will incident on a wall of a drum, rotating drum, clear? Then the density of the atoms or molecules collected on this plate will vary according to the speed of the molecules entering this drum, right? This is the principle, right? Now we will see how this entire experiment works, right? So when this oven is heated, the bismuth atoms will come into gaseous state, and they will come out of here through this very fine slit S2, right? Then this collimated beam of bismuth atoms will move in this direction, and now this drum is rotating continuously, right, in this direction. Clear? At very high speed. It means it means this slit will come in front of this incoming beam of atoms or molecules, right? Only for a very small, fractional time, right? During that time, these atoms, these molecules can enter inside this hollow drum. For the rest of the time, there is no way to enter inside the drum. Once the atom enter inside the drum, clear? And one more thing, that the temperature of this oven, this is fixed. It is T is a constant. It is not changing, because we know if the temperature will change, obviously the speed of the gas molecule will change. Clear? Because all the B RMS or B average or B most, they're all linked with the temperature, right? So temperature is fixed. This drum is also rotating at this speed, but it is uniform, right? It is constant. It is not changing with the time. It means after a fixed interval of time, this slit is exposed to the incoming atoms. So the atom will enter here. Once the atom enter here, now they travel toward this side, right? So you can see those atoms which are very fast, clear, they will immediately reach here. But those who are slow, they will take time. So during that time, this drum would have turned toward this side. It means the fast atoms, right? They will be reached here first, and the slow atom they will reach here. It means all those atoms which are fast, they will get deposited toward the right side of this drum, whereas all those atoms which are very slow, they will get deposited toward the left side of this drum. So this is the very simple way of collecting the atoms at this glass plate of rotating drum. So in actual experiment, IF Jartman and CC Co operated this entire experiment for 8 to 15 hours. Then after, they removed this glass plate and took the analysis of the atoms or molecules collected here, right? So then after their analysis, because the number of molecules or atoms of bismuth they collected here, it is directly proportional to the speed of those molecules, those atoms, right? So after the analysis of the density of these collected atoms, it was found that it was in very much experimental agreement with the theoretical predictions, this equation and these values, vrms, v most probable v, right? So this experiment then verify that this is the correct formula for the distribution of molecular speed, right? So I am hopeful that this entire experimental setup and working is very clear, right? So thank you very much.